Train longer, generalize better, closing a generalization gap in large batch training of neural networks, work by the Technion Israel Institute of Technology. It is common knowledge that more computing power and more data usually results in better models. To run large models fast, we need to increase the computing power during training. There are two ways to do so with current hardware: model parallelism, splitting the model into several workers, as done by Alex Krzyzewski, or splitting the data, in which each worker receives several samples, run back propagation, and pass the gradients to the rest of the workers. Data parallelism efficiency depends on the batch size. A known problem is that a large batch size hurts generalization. Keskar et al. Observed that even if the model is trained without any budget or limits until the loss function ceases to improve, the generalization gap doesn't vanish, and the big question is why. The open questions that we are going to examine are: what is the mechanism of this behavior? Is there an inherent generalization problem with large batches? Can we generalize better with larger batches? And can we reduce the wall clock time? We suggest the following hypothesis. During the initial high learning rate phase, the convergence behaves like random walk on a random potential, where the standard deviation of the loss difference asymptotically increases linearly with the weight distance. This is called an ultra-slow diffusion. The informal reason for this behavior, for any given gamma, is that for a particle to move a distance d, it has to pass potential barriers of height d to the power of gamma over 2, as proved by Marineri et al. We ran several experiments and projected their weight distance from their initial position into the same axis. This revealed the expected logarithmic increase of the weight distance with gamma equal to 1. Based on our initial observation on CIFAR-10 dataset, we suggest the following rules to improve generalization. 1. Use stochastic gradient descent with momentum and gradient clipping, and not more advanced optimization methods. 2. Adapt the learning rate by the square root of the batch ratios, stems for the covariance matrix of the gradients. And 3. Use ghost batch norm, a simple layer that mimics the small batch statistic when running with large batches. Using those guidelines, we can see that even with different batch sizes, the weight distances have some logarithmic behavior. Yet we have to increase the number of updates according to the batch ratio to close the generalization gap. We ran experiments on CIFAR-10 and ImageNet. The following table summarizes the importance of each rule. As can be seen, the generalization gap completely vanishes. Later on, Facebook published a paper with similar guidelines which proved that you can improve the wall clock time by a factor of 29 and train ImageNet in 1 hour. In conclusion, we observed no inherent generalization problem with large batches. Surprisingly, previous rules of thumb regarding optimization regime and specifically learning rate annealing schedule may be misguided. In contrast to common practice, good generalization results can be received from many gradient updates in any overfitting regime, in which the training error is low and the validations start to increase. This is further examined in our most recent paper, The Implicit Bias of Gradient Descent on Separable Data.